Since this is our first example of a continuous probability distribution, as opposed to a discrete one, let's compare properties of continuous and discrete random variables. For a discrete random variable, the probabilities must sum to 1, whereas for a continuous random variable, the integral of a probability density function must equal 1. Intuitively, this makes sense because the integral is defined as the limit of a Riemann sum. Similarly, for the expected value, with both discrete and continuous random variables, the probability is multiplied by little x, the value of a particular outcome, and then summed or integrated as appropriate. Here we see the graph of a probability density function for the standard normal distribution, which has a mean of 0 and a standard deviation of 1. We will use this particular normal distribution most of the time, since any other normal distribution can simply be shifted and scaled to obtain this one. Note that because of a bell shape, the majority of the area is within one standard deviation of a mean. That is, for z between -1 and 1, and nearly all of the area is within 3 standard deviations. This means that the outcomes of nearly all experiments that follow this distribution are between -3 and 3. The probability density function gives us the probability that a continuous random variable X equals a specific value x naught. But if we want a probability that X is less than or equal to x naught, then we must integrate the probability density function, which gives us the following definite integral for this probability. Unfortunately, we cannot evaluate this integral analytically, because there's no antiderivative of e to the minus x squared in terms of elementary functions. Instead, we must evaluate it numerically. For the standard normal distribution, this troublesome integral has been evaluated numerically for various values of x naught, and the results made available in tables, such as those that you can find in any statistics textbook. This means that if we have a random variable X that follows a normal distribution with a mean mu and standard deviation sigma, then in order to compute the probability that X is less than or equal to x naught, we must shift and scale x naught to map it to the standard normal distribution. The result of this shifting and scaling is the z-score, z naught, which is the number of standard deviations between x naught and mu. Then, if capital Z follows the standard normal distribution, the probability that capital X is less than or equal to x naught is the same as the probability that capital Z is less than or equal to z naught, which we can obtain from a table. We also see here how other probabilities can be obtained, using properties of probability and a symmetry of a normal distribution. Since capital X is either less than or equal to x naught, or greater than x naught, these probabilities must sum to 1, so we can use that to easily obtain the probability of capital X greater than x naught with the aid of a table. These next two formulas are most commonly used for the standard normal distribution, for which the mean mu is 0, so we can get probabilities involving negative values of x naught in terms of probabilities involving positive values, which are the ones published in tables. Finally, the probability of capital X falling within an interval is easily obtained in terms of two probabilities that we could obtain using tables. Here we can see how symmetry is used to obtain probabilities for a standard normal distribution. Note that the area of this portion, which is the probability that capital Z is greater than z naught, is equal to the area of this portion, which is a probability that capital Z is less than or equal to minus z naught. Also, it's because of this picture that we refer to these probabilities as left tail and right tail probabilities. We will use these terms frequently. The empirical rule is useful for estimating probabilities for any bell-shaped symmetric probability distribution, and in fact it is derived from the behavior of a normal distribution. The empirical rule states that if a random variable follows a bell-shaped symmetric distribution, then approximately 68% of its outcomes fall within one standard deviation of a mean, and then 95% fall within 2 standard deviations, and 99.7% fall within 3 standard deviations. The normal distribution can also be used to approximate the binomial distribution, since both are symmetric about their mean. In this case, the assumptions are less stringent than for the Poisson distribution. It's enough that n times the probability of success, p, and the probability of failure, 1 minus p, are both at least 5. To perform this approximation, we use a normal distribution with its mean and standard deviation equal to those of a binomial distribution that we wish to approximate. Also, because the binomial distribution is discrete, whereas the normal distribution is continuous, we have to be careful about left and right tail probabilities and use integers with half steps. For example, if we want to approximate the probability that capital X is less than or equal to 5, where X is a binomial variable, we need to compute the probability that capital Y is less than or equal to 4.5, not 5, to get it right. Here we see the approximation of a binomial distribution by a normal distribution. Since the parameters n and p satisfy the conditions given earlier, the approximation is quite accurate.